Critchley is not only the chairman, he's also the first speaker. He and Paul Marriott are talking about similar aspects of the same problem. So I'm going to chair the first two talks, and he's going to take over after the first two talks. So carry on.
Thanks a lot, John. And well done, people, for being here, and at least in most cases appearing to be showing signs of life. Competency is a real killer. So thanks for coming. And this is a talk, this joint work, and it says this is foundational, and you'll see it opens up into quite a wide variety of areas. It's a project four of us have been working on for some time, and Paul, one of the four, will be carrying on afterwards. What's the overall aim of what we're doing? Well, in our view, we've been doing this kind of stuff since the 1980s, and we do actually believe that information geometry has power and elegance, and we come from statistics. And the thing which is annoying us, perhaps I'm too easily irritated in my grumpy old man state of life, is that people aren't using it in practice. In particular, we have fancy, high-order, invariant asymptotics, and people don't use them. And we have lots of other interesting insights and applications from information geometry that aren't being picked up on. Unfortunately, there are a couple of little exceptions. This will work for the amendment for you. Oh yes, very good. Markov chain Monte Carlo recently has been using ideas of geometry, and Mike is giving the third talk. We'll give some examples and furtherance of that work. And along with John Coburn, a lovely English gentleman, Shinzo Waguchi, who is well known in the Chinese, the Japanese community, did this great way of handling model uncertainty locally and asymptotically, just by doubling the variance. Very elegant formula when you pick up the news. But with a couple of exceptions like that, people aren't getting this stuff, they're not using it. So what we decided a few years ago is to try and create some tools for practical problems of outstanding interest in statistical science. Outstanding both meaning they're still open problems and also they're important. So this stuff in red and italics goes together for the first couple of slides. And another way of doing it, a trick in doing it, is to have an operational, in inverted commas, universal space of all possible models, which I'll say a bit about in a moment. What are these problems? So one of them is what we call local to global sensitivity analysis. And if you ask yourself the one-liner, I say, what geometry is most suited to going seamlessly without any apparent effort from local to global? You will tell me, affine, yay. There you go. So that's what we do. There are two duly affine things in the information geometry. And fun enough, you'll see, I don't know how much time Paul will spend on this, but there's a -1 element in school of thought in mixture analysis. So that's using that, but not the +1. So we're going to use both in a standard information geometry way. Not in this talk, but in future work, and we've spoken about it elsewhere. Just give you some sort of flavour of where this is going before I lay these foundations. Handling both data and model uncertainty. We're all familiar with data uncertainty. Random samples won't be the same next time. But model uncertainty is obviously a very hot topic. And our way of dealing with that is by embedding a very natural thing. Inferencing graphical and related models. Well, as you probably know, may well know, there's lots of interesting graphical models nowadays. Now, the key things you may not know is that how they attach to the boundary is of fundamental importance. It's whether or not the natural parameters have an estimate, at least in a finite sense. So you can't avoid, if you think about it, some geometrical problems in a very widely used area of statistics. And then transdimensional and other issues in Markov chain Monte Carlo. So Mike's going to give an update on loads of stuff which is being done with he and his colleagues at UCL. And Paul and I are sort of working on our own line of attack, but very conscious of some issues that we can help address, we hope, with that. That's why we've been saying it now, so paint a picture, and we can maybe chat later or email or whatever. And finally, mixture estimation, which is what we're going to speak about. So we just chose one of them, and that's mixtures, and that's coming up in 25 minutes' time. Now, just to emphasise that when I speak today about a statistical model, I'm meaning a sample space only, well that's fair enough, but also just a set of distributions on it. And explicit are not required to have the same support. So just keep that at the back of your mind. That's a difference to usual. But the idea is to represent the inference problems that we face whenever a statistician can analyse data to help people answer their questions. We're going to embed them inside adequately large but finite dimensional spaces. The finite is so we can compute operationally. In these embedding spaces, what we're able to show is that the building blocks of information geometry are there. They're explicit, they're computable, and they're algorithmically usable. You can make them operational. So modulo a possible initial discretization for any random variable of interest, you get an operational universal space via the simplex, given there in display 1. Each vertex of the simplex having a unique label corresponding to representing the random variable, one of the values it contains, or the bin it sits in. Obviously, the multinomials themselves are the relative interior of this. There's a strict inequality for them. But one allows distribution with different support sets, and that's where the boundary comes in. For those who are on the technical side of things, extended exponential families obviously will play a central role here, so that's the underpinning stuff. Why bother? Well, I'll quickly paint a picture of statistical science, and you'll see within that the focus today is on perturbing a working model. The models don't come from nowhere, they come from a conversation normally between the scientist and the statistician. The scientist has the question, they take into account all the prior considerations, what the people in the area have known and written. Possibly with your help, they produce a prior if you're doing an amazing thing. So the model here, think of as the likelihood. That's your working model. That's you and your scientist best shot at describing the world. You collect some data, you choose your inference method, do whatever you like, and that pops an answer. It's a T method. But the obvious thing is, there's no unique way to do this. No one's going to say this is the only way I can formulate the problem. So perturbing the problem is pertinent, and then seeing how the answer changes is required to do a sensitive analysis. So the focus today will be on perturbing the model N. And it's often, not necessarily, it's often explicitly parameterized on this sample space only. So here's the agenda, to represent this working model N by a subset of delta K, and use information geometry of delta K, which is entirely standard, tensor often, and so on, to numerically, well, except for the boundary, numerically compute important features of M. What are these? Well, they include statistically important. That means they include the likelihood, the non-trivial, as we'll see, how adequate to first-order asymptotics, can we get any curvature-based dimension reduction. Time permitting, I'll cover all of those points, and Paul will do the last one. But the focus today, just for practicality, is on ideas or proofs. But there is an archive paper cited in both our conference proceedings, and that's got way more than either talk in it and other topics we won't cover. Okay, so we have to discretize. There's going to be some sort of trade-off. What's the key question? The key question is, for the inferential objects of interest, what do you stand to gain or lose by a particular choice of categories? I'm going to give you a couple of theorems which are reassuring. But first of all, here's an example of leukemia patient data. 43 survival times from diagnosis measured in days. Survival time measured in days. So survival time is a continuous thing, but the data is observed in days. And the question of interest here, what's the mean? So Z's model is exponential, that's the working model. But let's say you only observe a truncated value y, the minimum observed in t. So y becomes a one-dimensional curved family inside a 2D regular exponential family. And we've just chosen t to a reasonable but not perfect fit. This obviously illustrates 2 points directly. First of all, as I just said, the model is continuous, the data are not discrete. So this causes no loss at all in treating data as sparse categorical. They are sparse categorical. More surprising, perhaps, is that if you further introduce extra way of discretizing, a further level of coarseness, and only observe things to 4 days, then you basically don't change anything. Look at panel A, this left-hand panel. The circles, or the log likelihood for mu in the original scale, 1-day bins. The solid line are 4-day bins. But you can be forgiven for thinking the solid line is the piecewise linear interpolation of the values in the circles, but it's not. But they're visibly indistinguishable. Okay, so you don't necessarily lose as much as you might think you do by discretizing. That's the moral of that little story. Now, technically, what do you do? Well, the theorems show that you can make the loss arbitrarily small, and the key to doing that behind the scenes is to control the main conditional moments of the things of interest, but do so uniformly in the parameters of the model. So I'm going to get a bit fast. Don't worry, just, you can get hold of this if you want to. But the one thing I want to say here is, if your family has got a compact support, that's the key thing, and these gradients are uniformly bounded, then whatever epsilon you choose, whatever sample size you have, you can find the partition depending upon them, such that whatever data you get, whatever pair of values you're comparing, the parameter, the log-likelihood ratios are indistinguishable as between being continuous and the discrete. So C is the continuous thing, as in with the exponential model, or the truncated exponential model, D is the discretized one. So basically, the log-likelihoods, you can make them as near as you like. Theorem 2, a bit more technical, a bit more detailed. Very often, as we know, you're working with, in the working model, an exponential family. Well, great. Okay, it's classical information geometry. Small point, if you discretize a full exponential family, you may not stay full. But however, you can show that any loss of information can be inferentially unimportant, and all information geometry results in the 2 families can make arbitrarily close. So again, the key thing here is you just take a family and obey the standard regularity conditions in the Mari. S here is uniformly continuous, and its image S of chi, S of x, to be compact. And you can tell the roles these things are playing in the background. When I tell you the conclusion is that all happens if any epsilon some partition size depending upon epsilon. So that's the bin labels you choose in the partition pi. Then when you discretize, so pi theta is now the probability of being in bin bi under the parameter of theta. All the terms in a Mari, all 3 terms are the same to within the relevant order of epsilon. Just very quickly. Remember, C is continuous and P is discretized. The means, different order of epsilon, the Fisher information, epsilon squared. And what Shinichi doesn't like to call the skewness tensor, the symmetric tensor, is now called the cubic. The cubic tensor, order epsilon cubed. So you can control, you get your Mari structure embedded in the simplex to arbitrary accuracy of the appropriate orders 1, 2, or 3. Extension, I've got no time for that, but you can do this, go for infinite to finite. You need to be a lot more careful when you fill the spaces. So that's a quick version. There we go. Okay, now on to the meat of the thing. This extended geometry we're using. So our ambient space of the extended multinomials is actually a lot easier than you might think. What is information geometry? Well, the way we think of it now, because you've got a closed simplex, you have to take the boundary into account. Your problem's statistical context tells you the boundaries are important. There's a lot of reason for doing it this way. Well, of course, you can't use manifolds. You have to use the least manifold of the boundary. We've also changed support. So we've got manifolds of different dimensions. So it looks tricky, but it's actually not, because the geometries are duly connected, and they're both affine, the plus 1 and the minus 1. And that's enough to get everything. You know that we've heard it this week. Let me skip things. Closures have been widely studied, but in the infinite dimensional case, context here, I optimize the original can see order. He's taken a secret to see where it ends up. I'm going to show you by pictures what we do, which is take a whole family and see where the whole family ends up. So we follow the Amari structure. There's a nice book by Murray and Rice where they introduce the affine idea. Let's use an affine space. It's simple, it works, local developers integrated, and Paul extended that in '02. So remember that Manuel wanted to discretize the affine set of bins, and so the distributions of the branching probabilities, and this will be used notation slightly to conveniently identify the bin with its label. Okay, now, what is a -1 affine space? We've did that before. Here it is, essentially. It's a triple. It's a set A, vector space V, and an additional operator plus. Why? Well, V helps you move around within A by whatever the addition is. So the -1 case can hardly be simpler. The set A are all the sequences, vector if you like, but it's more elegant this way it extends. To all the sequences which add up to 1. These V is all going to add up to 0, and plus is just adding sequences. And so that's the affine space with around it. It's just like Rn if you like. It's the hyperplane of elements adding to 1. And of course delta K is just a -1 convex subset of that. You just chop things off, and it would have gone negative. But you just move around in an ordinary vectorial way. That is what the -1 affine geometry is. And that's connected in exponential family context with mixtures. Why? If you have the idea of what is a -1 geodesic, if you have the right coordinates, which are the mixture coordinates, the log density if you like, then you just add and that's it. So geodesic from A to B is just the line segment joining A and B in that geometry. Okay. We'll see the pictures in just a moment. The +1, okay, if you want to sleep, and you probably do, like, to be honest, I think I do, now's a good time to switch off, because it's going to be a bit more mathsy, techy than the other stuff. But if you're with it, let's go for it. This is the tricky bit, the +1 thing, you have to do it separately for each support. Remember, we're allowing different support. But the collection sets of distributions sharing the same support form what's called a superficial complex. Formal maths definition. Taken for granted by the nodes you know, this math you know. But they all fit together, different dimensions, in a nice elegant way. Continuity is defined topologically by that structure, basically. So a support identified with a non-empty subset F with the index set I, so it's a collection of values that random variable. F connotes face, as in face of the simplex, and we can't see this one. Each F has a separate +1 affine structure. Okay, that's why it's a bit more complicated. Other than that, it's straightforward. It's a set A, vector space V, an addition sign, now a bit more complicated. What is this thing? Well, A of F, these are all the positive sequences indexed by F. We have an equivalence relationship on it, which is proportionality. The set are just the equivalence classes. The vector space are just the real sequences indexed by F. Addition is take a base point and exponentiate element-wise. So think about, you see in a minute, pi's probabilities are exponential of theta times x, basically. An exponential family, or a base point, which is sometimes hidden in the underlying measure, and then e to the something times something. That's what the VI comes in. Okay. So back now, show you some pictures. I'm going to show you +1. The only thing I can show you on the screen is a trinomial case. But believe you me, if you're not, don't believe me, read the paper. What you're seeing now goes through in general. Okay. There's nothing in my sleeve apart from parameters. Right. So we're going to +1 geodesics in the +1 parameters. To make things concrete, I'm taking myself an arbitrary vector C, and X is trinomial with properties pi 1, pi 2, pi 3. It takes the value 0, 1, 2, pi nulls, and so on. We'll give some blue lines, which are the level sets in the mean parameter for C transpose X, and then minus 1 geodesics by definition. The black lines are plus 1 geodesics by definition, and they correspond to entire one-dimensional full exponential families where, here it comes, the properties are base point pi I times exponential or something, just the kind of equivalence thing. And this normalizing constant does what it says on the tin, it normalizes. It's just scales, so it's intimate to 1. Key fact is that we're going to see some minus 1 parallel blue lines and some plus 1 parallel black lines constructed just like that. So this C is the same as that C, that's the key thing. Well, standard Amari theory goes through, and everywhere fish are orthogonal. So this is where, as I promised I would, I glue together the plus 1 structure and the minus 1 structure, and it's via fission. Okay, that's the standard information geometry line that's happening. There's quite a lot going on here. Let's just start in panel A. So these are minus 1 geodesics, these blue lines in a minus 1 space. This sandwich shape is a representation of delta 2. These geodesics clearly is attached to the boundary. You just follow your nose and you get there. There's no problem. So they extend naturally to the boundary in the mean parameters, the minus 1 affine coordinates. There's no problem. These blue things are the same, but in plus 1 coordinates. So basically, pi I is not a log pi over pi naught. Pi naught is the base reference. These are clearly non-linear, and it's a point of bifurcation. Why? The value 2 is the value when it goes to this vertex here. So something funny goes on. So these are not linear. What are these black ones over here in panel D? Well, they're all parallel, they're all straight. These are plus 1 flats. That's what exponential families are, one-dimensional. A p-dimensional full one is a p-dimensional flat. Okay. You can move these parallel to each other, change the base point, and then look at the image over here now in minus 1 space. Well, the curve, that's no surprise, because it's a nonlinear transformation. What are the limits? Well, as I'm going to the left, this is the relative interior of the simplex. As I say, you can't see them all at once. I'm going to show you the 2-dimensional bit, or the 3 one-dimensional bits, and the 3 0-dimensional bits. As you go to the left, they go to this edge of the simplex. As you go to the right, you get all of this edge, vertices included, and all of the bottom edge. So this is the clue, visually, to what's going on in this rather complicated simplicial complex. And you can put a, what happened there? There you go. You can do this dashed line infinity to try and show you what's going on intuitively. Okay. But that's what you need from the theory side of a triangle. From the practical side, this is the important pattern. How does my exponential family attach to the boundary? If I'm estimating a graphical model using a family, I need to know that. Where does it attach? Where does it reach? Where does it get to? Okay. I'm going to have to choose my topics quickly. Let me just say that all of your reflexes on the shape log likelihood go wrong in this sparse simplicial setup. Standard chi-squared approximation to deviance out the window. We need something else, which we can provide, but again, that's not today's talk, and the work's not entirely finished yet. But you can understand it very simply this way. What you do when you disclose is the data become counts from a multinomial. Some of the counts are 0, z is 0, some are positive, p for positive. Now together, that's all the possibilities. The log likelihood, okay, so is a term. What's the observed face? It's the face found by those vertices indexed by p. You've got at least one observation in each of those values. The unobserved face is the complement. The log likelihood is nice and well behaved in the observed face. We'll give you lots more detail about that when it comes to mixing. Away from it, it's strictly decreasing in the normal direction to the unobserved face. Otherwise, it's entirely constant. There's minus 1 flat in huge affine spaces. 5 minutes to go. Thank you, John. So that's going to be enough on that. So what I'm doing now is, if that agenda I set out at the beginning, instead of structured and work through the basics, lay the foundations, that's what we're doing. So that's what one blanket looks like. All the action in the observe phase is sort of textbook stuff. Away from it isn't. Spectrum fish information, this is really neat. Very simple stuff. We'll all have done it, I guess. Interlacing eigenvalues sometime in your life. You'll almost certainly been exposed to them. The big thing is that the Fisher information is a diagonal matrix with a rank 1 correction. That means that its eigenvalues interleave the diagonal elements. What are they? These are just the bin probabilities. What are they? Well, if your working model's a normal one, some of them are exponentially small compared to the rest. So that's going to come through in your spectrum. So that means that you, with things you can observe and do observe, give you information about eigenvalues without any effort. And so dimension reduction, you kind of see it on the screen. You kind of know what's going on. Again, the whole idea, remember, is to give people tools they can just use and see. They don't need to know the maths, but they can tell them the geometry intuitively. They know why doing what the screen tells them to do is kosher. Okay, so I'll skip that. Closure. No, let's see if it goes. Okay, so you've got the full exponential family embedded in a high-dimensional sparse simplex. An important question is to identify its limit points, how it connects to the boundary. Panel C showed that generically at least, one-dimensional exponential families like vertices. Why is that? Well, it means exponential of x goes to plus infinity at one end and 0 at the other. So one of these terms, one of these bin probabilities will dominate. If it's time values, the maximum, then it'll go to the face span of those times. So you know exactly what's going on and why it's going on. Finding them, our way of doing it is just finding redundant linear constraints. You can convert it by duality to an extremal point problem, standard convex body thing. You can do it, it's computable. Another very, very insightful and operational Charlie Guy, great paper in 09, EGS, readers, directions of recession that appeals to you. That's his way of doing it, does the same thing. So we can compute these things, that's the key thing. Now this takes the pools, I have to do this. The -1 convex hull, exponential family is of great interest. Why? It's all the mixtures of it. Have a working model, it's exponential family. What are all the mixed distributions? It's just a -1 convex hull in that family. So widely used in practice. You know, the ICMS, one of our major math centres in Britain, and indeed in the world, had a meeting just about mixed models recently. They're that important and that current topic. Well, Paul's going to speak all about that, but the key thing I want to say here is the main result underlying it, or one of the main results, is that, well, you may not know about total positivity, but the function of x and y, exponential of x times y, is something called strictly totally positive. Well, we have exponential families, so we have exponential, so that should be exponential of x times of theta times, which is just even a one-dimensional family. What this tells you is that even a one-dimensional exponential family, which is a +1 flat, it's not only -1 curve, it's -1 space filling. It's a maximal dimension. You take the tiniest cut of it, the tiniest open interval, it's a full dimension. That might lead to think, oh dear, I can't do dimensional reduction. But as Paul would say, you can. Right, let me just wind up by saying that we go to this one. The same data we had before, log clearly skewed, gives you the idea